So let's talk about watts and power and energy. So in general, power is applied to provide an indication of how much work can be accomplished in a specific amount of time. So power is the rate of doing work. Energy is measured in joules and time is in seconds. Power is actually measured, you know it as watts, but watts are really just joules per second. So 1 watt is equal to 1 joule per second. Remember, you saw joules when we talked about energy and voltage, when we defined voltage as the amount of energy it took to move charge. This is the same energy that we were talking about. So power is that energy divided by time. Another way of looking at it is it's the voltage times the current. So the power delivered to a circuit is the current that the circuit draws times the voltage. Another way of looking at that, if we were to take our Ohm's law equation, remember, E is equal to I times R. So if we replace E with I times R, we get I squared times R. And in the same equation, if we take I instead and replace it with its Ohm's law equivalent, E over R, or V over R rather, we get V times V over R, or V squared over R. I think you're starting to see where some of those equations came from in our Ohm's law wheel. So if we were to calculate the power delivered to our motor here, for example, we would multiply the voltage times the current, or 120 volts times 5 amperes, and what would that be? 600 watts. So the power associated with any supply is not simply a function of the supply voltage, but of the supply voltage and the maximum current rating. And I'm going to go back to our Ohm's law wheel here and explain where a lot of these equations came from. Let's look at the Ohm's law wheel again, and this time let's think about where these equations have come from. So they came from two main formulas. They came from Ohm's law, which says that V is equal to I times R, or I is equal to V over R, or R is equal to V over I. And from Watt's law, which basically defined power as voltage times current, or current is power divided by voltage, or voltage is power divided by current. So we can find any of the other equations this way. So let's say we're looking for voltage. We find it here is P over I, that's right here. It is I times R, which is right here. We also have it in terms of power and resistance. Now how we got that is that in our power equation here, if we substitute, let's see, P equals V times I, if we substitute I equals V over R, we get P equals V squared over R. And if we solve for V, we would multiply both sides by R. And then if we take the square root of both sides, we get V equals the square root of P times R. Actually, I said that backwards, didn't I? And that's the equation there. Okay, so let's add another equation here. P equals V squared over R, and V equals the square root of P times R. Okay. Now, let's go the opposite way, and let's say in our power equation, P equals V times I, let's say instead of using this equation, we're going to use V equals I times R. So we're going to substitute for V, I times R times I. So P is equal to I squared times R. So there's another equation. And if we wanted to solve for the resistance, the current. Let's solve for the current here. We're going to divide each side by the resistance, and then take the square root. Whoops. Take the square root, and we'll just add our equation over here. So I is equal to square root of P over R. I, that's here, and then P over V, and then of course V over R. So we've looked at all three of those. Okay, I guess we also have all of the power equations here too. We've got, of course, V times I squared R, and V squared over R. So we now need to find our resistance equations. So of course we have the Ohm's law, V over I. It's right here. Now let's take two equations. Let me get rid of a couple of these. Let's take this equation and this equation, and we're going to solve each of those for the resistance. So here, R is equal to P over I squared if I divide both sides by I squared. And here, R, if I multiply both sides by R, I get R times P equals V squared. And then divide by P, V squared over P. That's right there. So this is where all these equations come from. However, they are really nothing more than V equals I times R and P equals V times I. Let's work some power problems now. So power is equal to voltage times current. However, if we use our Ohm's law relationships where V is equal to I times R, or I is equal to V over R, and we substitute either for V in our equation or for I, we get these other equations. P is equal to I squared times R, or P is equal to V squared over R. So let's look at our first problem here. The power delivered to a DC motor if we apply 120 volts and the motor draws 5 amps of current. Well, P is equal to V times I. So we have 120 volts times 5 amps of current, or 600 watts of power. Okay, the next problem, we want to find the power dissipated. You're going to see all these words a lot. Power delivered, power dissipated, power absorbed is another way of saying this. Basically, all of them mean a very similar thing, and you will hear them used in a lot of cases, whether, sometimes they can't really be completely interchangeable, but you'll hear them in pretty much every case. Okay, so we have a 5 ohm resistor, and we have a current of 4 amperes. So since we have current and resistance, I'm going to use this equation right here. So P is equal to I squared times R, where the current is 4 amps and the resistance is 5 ohms. So that gives us 80 watts. Now, if you don't remember all the different equations, remember we can take resistance and current and find what from that? Voltage, right? V equals I times R. So we could take our 4 amps and multiply by the 5 ohms and get 20 volts. And then we can just take our power equation, which is V times I, and multiply our 20 volts by the 4 amps, and guess what? We get 80 watts. So you don't necessarily need all of the other equations. You can get by with these two, okay? You don't need any others, really. It's nice to have, but it's not always necessary. Okay, let's look at another problem. We have a calculator with an internal battery, and we know that it draws 0.4 milliwatts of power. What is the current demand from the supply? Okay, well, when we're looking for current or voltage, we're going to have to divide the power by whatever we have, the other one. So the power divided by the voltage in this case. So we've got 0.4 milliwatts divided by 3 volts, and that gives us about 0.133 milliamps, or the correct engineering notation would be 133 microamps, because remember, we need that number to be between 1 and 1,000. So if the calculator is rated to operate at 500 hours on the same battery, what is the ampere hour rating of the battery? So remember, we found that the life of the battery was the ampere hour rating divided by the amount of current we needed to supply the circuit. So if we're looking for the ampere hour rating, we would just multiply the life of the battery by the current. So we've got 500 hours times the 133 microamperes, and that means that the ampere hour rating should be about 66.7 milliampere hours. Okay, so 2 more problems. Let's work 2 more. So a 20 kilo ohm resistor has a rating of 100 watts. What are the maximum current and the maximum voltage that can be applied to the resistor? Well, for this I am going to use our equations where we had P equals V squared over R and P equals I squared times R, and I'm going to solve for V and for I in each of those equations. So for this equation, I would multiply both sides by R, and then I have V squared. And then if I take the square root of both sides, I'm left with just voltage on the right-hand side. And my equation here, if I divide by the resistance, I have I squared, and if I take the square root of both sides, I'm left with just I on the right-hand side. Okay, so V equals the square root of 100 watts times 20 k ohms. So the maximum power, maximum voltage we would see there is 1,414 volts, or correct engineering notation would be 1.41 kilovolts. For our current, P over R would be our 100 watts divided by 20 kilo ohms. So our current, our maximum current would be about 0.0707 amperes. And again, correct engineering notation, move the decimal 3 places over to the right, 70.7 milliamperes. Okay, so we're looking in this next problem, what is the total horsepower rating? Now, horsepower we haven't talked about, but horsepower is the same thing as power, and we'll just use a conversion factor. It's just a different way of saying power. So 1 horsepower is approximately equal to about 746 watts. So we're going to work this problem just like any other, and we're going to find the power in watts first. Just going to multiply the current by the voltage, and we get about 7,200 watts. Now in horsepower, 7,200 watts. We want to convert that to horsepower. So 1 horsepower is equal to about 746 watts. So putting the watts on the bottom cancels the watts out in the 7,200, and we'll be left with just horsepower. So when we divide 7,200 by 746, we get 9.65 horsepower. Now let's talk about energy. Power is the rate of doing work. To produce energy, it must be used over a period of time. Now this is what you're billed for when you're billed for. A lot of people say your power bill. It's actually your energy bill, because it's your power bill times, it's your power that you're using times the amount of time you're using it. So you're not just billed for turning on your clothes dryer. You're billed for turning on the clothes dryer and running it for an hour. So when you get your bill, you're actually billed in kilowatt hours, which is power times time. So the energy lost or gained by any system is determined by the power times the time, like I just told you. So energy in watt hours is just strictly watts times hours. However, you're billed in kilowatt hours because we use a lot more than just watts, right? We use thousands of watts. And so the energy that you're billed for is kilowatt hours. Still, it's watts times hours, but we'll just divide by 1,000 to keep with our kilo prefix. Okay, so to get some sense of that, 1 kilowatt hour is the energy dissipated by a 100 watt bulb in 10 hours. So you use 1 kilowatt of electricity every time you have a 100 watt bulb on for 10 hours. Did you know that? Hint, you might want to replace a few bulbs with LED bulbs to save you some money, and we'll work on that a little bit later. The kilowatt meter is an instrument used to measure the energy supplied to your home or to your business. And it used to look a little bit like this with the dials, right? I don't know if any of you remember seeing this, but you had a person who would come out to your house every month and actually read this meter, and then the company would compare that to what you had before, what you had used before, and then they would know how many kilowatt hours you used over the course of the month. Now, most of the meters are, of course, digital, and a lot of them are smart meters, so they can actually read them from a little bit farther away than your home, which I'm sure the people reading the meters are happy about, because they don't have to encounter the dogs in the backyard anymore. So let's talk about energy usage. The average yearly use of kilowatt hours has grown substantially since the 60s and 70s. And really, that's because our energy cost got a lot lower, and we just need a lot more energy now. We run so many things around our home that we can't do without energy anymore. Here are some typical wattage ratings of some appliances around your home. If you want to take a look and see what's using the most energy in your house, a lot of people zero in on this electric range. So that's the self-cleaning function of your oven. If you have a self-cleaning oven, basically it cranks the temperature up for several hours and burns everything off. That's what they mean by self-cleaning. But if you don't use that self-cleaning function, it doesn't use quite as much energy as this. Your clothes dryer uses a good bit. Your air conditioning unit uses a lot. If you have an electric water heater, you're using a lot there. But basically, it's how long you're using it, right? So we're going to work some problems and take a look and see what kind of cost is involved in using that energy. Let's calculate the energy, the cost involved in running a PC. So remember, energy is power times time, and that is what you're billed for. So we're going to step through the process of figuring out how much it costs us to run this PC for 4 hours. Okay, so the PC draws 78 watts of power. So we want first the power in kilowatts. Well, all we have to do is take our wattage and divide by 1,000 watts to get kilowatts. So that's 0.078 kilowatts for our PC. The time in hours. Okay, so we're assuming 31 days, 4 hours a day. So 31 days times 4 hours per day. And our days will cancel out here because we're dividing days by days. And we get 4 times 31, which is 124 hours. Now the energy in kilowatt hours is just the 0.078 kilowatts times the 124 hours. So 9.67 kilowatt hours is what we get there for the energy. And then the cost, we just take that and multiply it by the cost per kilowatt hour, which is 11 cents. So my 9.67 kilowatt hours times 0.11 for 11 cents means that it costs us about $1.06 to run that PC. Okay, an air conditioner. Let's look at an air conditioner. That's a different story, right? It's going to draw a lot more power. So if we use the AC on the 4 hours a day for the 3 hottest months of the year, June, July, and August, that means 92 days total. How much would it cost if the cost per kilowatt hour is 17 cents? Okay, so we're going to do basically the same thing. 2160 watts is the same thing. Oh, I left off my 0 there. Is the same thing as 2.16 kilowatts. And if we are using it for 92 days times 4 hours per day, that's going to be about 794.88 kilowatt hours. And then we're going to multiply that by 0.17 cents. So it's going to cost us about $135 for the summer. That may be a lot, but you know, it's either that or be really hot. So you can make your decision based on that. Now, if we increase the cost per kilowatt hour to 22 cents, what would that do to the cost for the whole summer? Well, we have the same amount of kilowatt hours. So I'm just going to bring that back down here. We don't have to recalculate that. But this time I'm going to multiply it by 22 cents instead. And I see that that is going to cost us about $174. So what's the difference? It's 5 cents, right? 5 cents. But 174.87 minus 135.13 for the entire summer is a difference of about $40. So it does add up. So you want to make sure that you're paying attention to your energy bill. And when these price increases go up, even if it's just a couple of cents, it's going to make a difference in your bill overall. Okay, let's talk about the maximum capacity for a minute. If we have a house supplied with 120 volt, 100 amp service, what is the maximum power we can use at one time? Well, again, it's just P equals V times I. So we have 120 volts times 100 amps. So that means we have about 12,000 watts we can use at one time, or 12 kilowatts in engineering notation. So we want to know, can we operate all of these loads in part B all at one time? Well, two 250 watt televisions, that's a total of 500 watts right there. And a 3,000 watt clothes dryer, And 10 60-watt bulbs is 10 times 60, or 600 watts. And we have a 2400 watt electric range. A 2 kilowatt air conditioner. Now 2 kilowatts is 2000 watts. You either need to have everything in kilowatts when you're adding, or you need to have everything in watts. So pick one and stick with it. And then we have a 1000-watt steam iron. So if we add all these together, what does that make? We've got 3500 here, another 33,000 here, so that's 6500. So we have about 9500 watts, or 9.5 kilowatts. Well, that's definitely lower than 12 kilowatts, so yes, it's safe. Okay. Now, if we use all these appliances for 2 hours, how much energy is converted into kilowatt hours? Well, we've got 9.5 kilowatts times 2 hours. So that would have to be 19 kilowatt hours. I'm going to take off that R. Kilowatt hour. And again, the cost of using those appliances, if we have a cost of 12 cents per kilowatt hour, means it's going to cost us about $2.28 for that 2 hours if we have all of this on. So you might want to start thinking about turning some things off from time to time. Now, the energy costs in the country, this is a fairly old graph, but you can see that North and South Carolina, our energy costs are pretty low compared to the rest of the country, particularly for Duke Energy. And when you get to California and New York, of course, you're paying a premium for electricity there. So you might want to check and see what you're paying per kilowatt hour on your bill the next time it comes in. Just take the amount you're being billed and divide by the kilowatt hours, and that gives you a good general idea. It's not exactly that, but that gives you a good idea of how much you're paying per kilowatt hour. And then if you want to look at some cost saving measures, you can do that as well. So let's talk about efficiency. When we apply some sort of energy to a system, we're going to get some energy output, right? But we're also going to store some energy in that system, and we're going to lose some energy in that system. We're almost never going to get out what we put into the system energy-wise. And this is what we look at in terms of our efficiency rating. Our efficiency is the output divided by the input. Basically, we're looking for a percentage. We're never going to see 100%. But you know, if you got 80%, maybe that's really good. So let's look at our energy output. Okay, so here we're looking at a system where you have a turbine, a gear train, and a generator. And this is generating the electricity that's going through the transmission system and then ultimately to the load to supply power, right? Or to supply energy to a client or a customer. Now, the gear train has an efficiency of something, you know, maybe it's 20%. The generator has an efficiency, maybe it's more like 70%. And then the transmission system has yet another efficiency. Well, the efficiency of the entire system is actually the product of all three of those. It's not, you don't add them together, you actually multiply those efficiencies, and you really see the effect of the least efficient system in all of these. So let's work a problem so you can see how this works. Let's work some problems with our efficiency equation. Now, efficiency is defined as the power output over the power input times 100%. Now, I'll say this is this portion of our equation, that's a ratio, and it's somewhere between 1 to 0. Okay, it's probably never going to be 1. it's going to be somewhere under 1, okay? And then we multiply by 100%, we get a percentage. So it's never going to be 100%. It's going to be something less than 100%. Okay, so and power out and power in, they can be in watts or they can be in horsepower. It really doesn't matter. As long as you use the same units on the top as you do on the bottom of that fraction, it really doesn't matter. Okay, so what is the efficiency of a dryer motor that delivers 0.8 horsepower when the input current is 4 amps and the input voltage is 220? So when a motor delivers power, that's the output. And you're given that the input current and voltage is 220. So those together are going to give you your input power. So Pn is the current in times the voltage in. So we've got about 880 watts that we're applying to the system. Now the output power is given in horsepower, so I'm going to convert to watts. 0.8 horsepower is 736 watts per horsepower. So the output power is about 596. 596.8 watts. So the efficiency, which is the output power over the input power times 100%, would be our 596.8 watts over 880 watts. And that gives you times 100%. Let's go ahead and put the 100% in there as well. And if we calculate that, we should have about 67.82%. So it's a pretty low efficiency, I think. Okay, in the next problem, we're now given the efficiency and that the input voltage is 240 volts, and we've got the output power here. So we're looking for the input current. Okay, so basically we need to know what the input power is, because with the voltage we can find the current. Okay, so we have an efficiency of 76%. So remember I said that without the times 100, that's actually a ratio. Okay, so the efficiency, you can think of it as 76%, or it's just 0.76 times 1, so depending on what you're looking at. Okay, so if the output power is 3.6 horsepower, I'm going to convert that to watts. We don't really have to. We could leave it in horsepower if we wanted to, but eventually we would convert it to watts to get our current. So I'm just going to go ahead and convert it now. 746 watts per horsepower means that we have about 2,685.6 watts. So if the efficiency is the output over the input, then if we solve for the input power, multiply both sides by the input power, divide by 0.76, we get the output power divided by 0.76, and we just found the output power was 2,685.6 watts. So the input power would have to be 3,533.68 watts. To find our current, we take our input power, divide by the input voltage, And that means that we would have a line current of about 14.72 amperes. So that was kind of a two-step problem there. Now let's talk about total efficiency of a system. Efficiency of a system is going to be the efficiencies multiplied throughout the system. So let me show you kind of how that works. We have a 2 horsepower motor that drives a sanding belt. And if the efficiency of the motor is 87% and that of the sanding belt is 75%, what is the overall efficiency? Well, the overall efficiency is going to be the efficiency of the motor times the efficiency of the sanding belt. And I'm going to actually use the ratio here. So 0.87 times 0.75. And I find that the overall efficiency is 0.65, which if we multiplied by 100%, that would be 65%. This and this are the same thing. This is the percentage, this is the ratio of this to 1, and this is the ratio of this to 100. It's really the same thing. Okay, we have pretty much the same problem here in part A of 18. What is the total efficiency if the 3 efficiencies of our 3 systems in cascade or in series or in order, however you want to call that, are 93%, 87%, and 21%. Well, the total efficiency is going to be 0.93 times 0.87 times 0.21. And what we find is the resulting efficiency is 0.17 or 17%. Notice that is lower than the least efficient system, right? And that's what you're going to find. It's the least efficient system that has the most impact on the overall efficiency of the system. So if we replaced that system with a system that had the efficiency of 80%, what would that do to the overall efficiency? Well, let's recalculate. We're going to keep our 93% system the same and our 0.87 system the same and replace that last one with a 0.80%. And here we see that now our efficiency is about 65%. So just by replacing this least efficient system with a much more efficient system, we have gained a lot of efficiency for the entire system.